Okay, I guess we're live. Who's here?
Okay,
I can see 4 people
I guess
watching.
we're live.
Oh, wait a minute. I'm trying to volume down. Okay. Right. Can we all hear? Can everyone hear me? Hello? Can everyone hear me? Let's see. Okay, until somebody... Okay. Alright, 2 people watching now, and I'm one of them. Okay, that's not great. Okay, let's just get started, and let's see what happens. I'll just close that out. So, in the last class, we built up a neural... We did not build up a neural net. In the last class, I'll show you, we built this thing here, which is basically just a block that drags a stick off to the side and off the world. So the next stage in this is to try and make it kind of intelligent. So let's do that. So first off, we need to talk about what is a neuron and how does a neuron work. So a neuron is basically, you've got like 150 trillion of them in your brain there. A neuron takes in a load of inputs, so there's a load of connections into it, and it decides, it looks at the detail that's coming from those, and it tries to add them up to make an output. So it decides like, okay, oh, I better look at that, and that triggers an output. So we need to create something which does that as well. And this is the demo that I built. Here we go, look at that. It's getting better and better over time. How do we do that? How do we make something that can do an output and learn? Let's start on that. Okay, so we'll start with this robot here. So I'm just going to copy last week's work to sticktree.js and open it up. Let's see. Looks like it's all readable. Alright, so what do we need to do? Let's see. Well, the first thing we need to do is we need to know some details about the stick. So we need to know, for example, where is it? What angle is it at? Is it moving? How fast is it moving? So let's have a look at that. So inside the loop callback, we're going to do something here. The loop callback is the loop that runs every time something moves on the screen or moves in the world. This loop gets called. So we want to know, like, has the stick moved in a way, and what do we do about it? Right. So we're going to create a value called inputs, or imps, inputs. Current data about the stick. So we're interested in where is it, and if we look up here, we created an object here called objs in the last one, which contains the ground, the robot, the stick, and constraints. We're interested in the stick, so objs.stick is what we're interested in. objs.stick. And it contains various things. Now, just to have a look at what it contains, I'm going to do this. So window.objs equals objs. Now, what am I doing here? The objs here is contained within this. It's constrained by this thing here. So it's contained within that. It's not accessible outside it. We need to be able to look at it. So I'm adding it to the window object itself. So let's view, inspect. So right click, inspect, and go into console. Now I want to look at window.objs. So we'll reload this now and see what happens. If I type in window.objs, it's undefined. It's undefined because I'm looking on the wrong page. I should be in stick-3, the new one. Oh, because I just... Alright, stick... We also need the HTML file. Stick3.html. And we'll just edit that so it links to the right JavaScript file. Okay. Now, if I reload this, then we got that again. But now we can look at the objects. See that? And that's the objects as they were at a certain point in time. But let's look at the stick inside it. In the stick, we can see it's got lots of different values. For example, the angle here. That angle is important. The way you measure an angle in computers, in maths generally, is it's not 90 degrees, 180 degrees, 360 degrees. That's the human way of measuring things. And that goes back to the Babylonians, I think, came up with that. But we measure, in maths, you measure it using pi. So how many times, like if you remember the circumference of a circle is 2 pi r. Or another way of looking at it is diameter multiplied by pi. So the radians, which is the amount of pi that you've traveled around, is if you just look at the diameter of something and then you measure all the way around, you could say that here at the top is 0, on the right is 1.57, which is half of 3.14, and on the left is minus 1.57. So that's what we're looking at here. Minus 1.5 is when it fell over. It fell over to that side, so minus 1.5. Let's look at that again, and I'm just going to reload that. And now I've caught the object before it fell down too far. So we can see the angle here is minus 1.6. Is it still? Do you know what I'll do is actually in the JavaScript, in that loop where it says window.objects equals objs, I'm actually going to output .log objs.stick dot, so there's objs.stick, and we want to look at the angle. So this is going to be outputting constantly, like over and over and over. Let's have a look at that. So we've just watched it fall over in numbers. So it started off at 0, which is straight, and then you can see it actually fell over gradually until it was slightly over 1.5. So it's a little bit over flat. But we're interested in that number because if you think about who else is on this? Oh, hello, Gangster JF. If you think about how would you balance a stick? Well, you're interested in, if we take it like, I've got an Allen key here. If you're balancing this, what are you interested in? You're interested in what is the current angle at it, in which case you want to go over to the other side. You're interested in how fast is it moving at. So if it's moving a little bit here, you don't want to go like that. You just want to go like a little bit. So we're interested in the angle, we're interested in the X position, we're interested in the velocity of it. There's a few different things we're interested in. So I'm just going to write those in now. So we've seen how to write that. It's objs.stick.angle. Oh, sorry, we're talking about X at the moment. X. And then it's actually position.x in this case. And then the position, we're actually interested more in how off-center it is. So the center of this screen is 400. So I'm just going to subtract 400, which will give us a center then, like, of the object of 0. Right, and then we know we want to know the angle, objs.stick.angle. I'm playing Universal Paperclips while watching the stream. Good man, take over the world and the universe. And then we want to know the angular velocity. So the difference between velocity and angular velocity. Velocity is how fast is it moving in a direction. Angular velocity is how fast is it turning. So it's not just what angle, but how fast is it turning. We're interested in that, angular velocity. And that's objs.stick.angular velocity. And we're also interested in the velocity. X. In the x velocity. We're not interested in how fast it's going up or down, just in x. Okay, now let's output that. Console.log inps. So we can watch what happens as the stick falls. That's cool. So we're seeing the x position move. We're seeing the angle is kind of like it's all the same now. The angular velocity is around, well, it's sped up there as it fell off the world, and then the velocity of x is almost constant as it falls off the world. It's just kind of constantly moving in the same direction because there's no friction. If we were watching y, we'd see that increase as it just speeds up downwards. I'm covering myself in grey. Okay. Alright, so we now know some information about that. So what are we going to do about that information? Well, I'm going to write a little piece of pseudocode. Now, pseudocode is when you are going to... Well, let's look at this code first, right? This is the set velocity that we had last time. It's the reason why the whole thing is moving. Now, what we want to do is actually... we want to still move it, but we want to move it to a certain output of a neuron. So we want to say that it moves this direction in x, that direction or that velocity in x, plus or minus. So I'm going to change this so it's output. Right. Output. But what is output? Well, output is going to be a calculation that we run on a neuron. So we need to create that neuron. So a neuron. Now this is kind of like throwing a whole jigsaw down and having it all fall into place. I'm trying to explain a lot of things at the same time. So we'll say that I'm going to write some pseudocode first. Right. Calculate neuron output. Now I'm just going to say that to begin with, the output is equal to 0. All right, just so that this will work if I reload this. So in this case, the robot is not going to move. It's not moving. And you know what? It'd be interesting if we put that stick off a bit. So I'm just going to move the stick a little bit. Let's say 59 here. No, the Y should be left alone. We're going to move the X to, let's say, 4 here. And 6 here. No, we'll just make it a bit more. Yeah. Okay, 5.5. So it's just slightly off. That's just going to fall over. There we are. And it falls over. Okay, that's what we're interested in. We're interested in stopping it from falling over. Let's reload that again. Okay, how do we stop that from falling over? So first off, we need to calculate the neuron output. And then we set the velocity equal to the output. So what is the output? Well, first off, let's look at a neuron. Now, I'm just going to get a picture of a neuron so we can talk about that again. Alrighty. So let's look at this again. So we have the dendrites, we've got the neuron, and then we've got the axon that leads off to certain terminals. Now we're interested in the dendrites is our inputs. So that would be x, angle, angular velocity, and velocity. So we'll say that each one of these is one of these inputs. And then the neuron is going to do a calculation and it's going to output that calculation. So we're interested in that. Let's set that up. So outside the loop, So you can see we've got the loop callback here. Outside the loop, as part of the initialization, we are going to create the neuron. And what is in a neuron? A neuron has inputs, which are our dendrites. A neuron has weights. Now, to explain the weights, let's say angular momentum doesn't really matter all that much. Well, in that case, we have a very low weight on the angular momentum input. So let's say it's that one there. It just means it doesn't really listen to that very much. Now, in computer terms, we do that with a calculation with a very low number. So 0.001, that kind of thing here. But we're not going to set the number. Well, we're going to initialize it with a number, but we're not going to say this is the number forever. It's the point of a neural network is that it's going to figure it out for itself. So we've got weights of various kinds. Then we have velocities, and velocity is tied to momentum. These concepts have to do with learning. Okay, so let's say you are learning to catch a ball. Somebody throws a ball at you, you put your hand up, but the ball goes over. So you figure out, you know what, if I move my hand in this way, off to the left, would the ball hit it this time? So the ball comes at it, and you measure the distance between the two, and you realize, do you know what, it's actually further away. So you kind of punish it in your mind, you punish it, and you just think like, that was wrong, so I'm going to reverse direction. And then you figure out eventually that, you know what, you move your hand gradually up in this direction, and that's what you're doing there is you're using velocity. You're saying, well, actually this direction gets righter and righter the further I go in that direction. That's your velocity. The momentum is that if you change your mind and decide like, you know, I'll try this way, and then the ball comes and misses again, and then the next time you just realize, well, when I was going in that direction, that's your momentum. When I was going in that direction, it was working. So I'll go back to going in that direction. Well, it's actually more like I'll go in this direction, but the momentum pushes a little bit anyway in that direction. We'll figure it out. Let's go with it. Okay, so inputs. What do we need inputs? Well, we already know it's going to be x, angle, angular velocity, and velocity. But I'm not going to just hard code them in there. The only one I'm going to hard code in there is something called a bias neuron. Now, the bias is a very special value. In this particular case, it's not going to make much of a difference, I think, but it's important to always have a bias in there anyway as an input. A bias is basically if we're doing multiplications of numbers in order to get an output. Let's say you want to get an output of 1 when all the inputs are 0. How do you do that? You can't do that because no matter how high you multiply the 0 by whatever number, no matter how big the multiplication is, the output is always going to be 0. So we need what's called a bias input, and the bias will always be 1. And that is going to give you the right number in the output. Right, so let's see, we've got the bias, we've got weights, we've got velocities, and we've got momentum. So let's see what happens here. With the weights, we want to initialize that. So I'm going to initialize it with, just copy this here. So we've got x, angle, angular velocity, velocity, and bias. So that corresponds to these and the bias. Okay. Now, I'm going to do something special to this later on. But for now, I'm just going to set them like that. The next one is velocities, and we're again going to start off with the same values. Okay, and then momentum. Now momentum is different. I'm going to start that off as 0. Doesn't really matter. I could use 1 in this case as well. It's going to get adjusted over the learning. So in this case, we are not currently learning. We are just setting up values. Right. Now, in the inputs, what we want is to calculate the neuron output, we first have to set up the inputs. We basically need to fill in the details into each of these inputs. So let's go through that. Okay, so for every key in this object, so object dot keys of inputs. So for every key in this, we want to do, so K for key, we want to do a certain thing to that key. We want to say the neuron dot inputs K is equal to imps K. So what we're doing here is we're filling in the values of, we have the neuron, and we're filling in the values with what we figured out from the current position in the physics world, like in what's actually happening in that thing there. So we're taking the values of this stick and we're sticking it into the neuron. Okay, and then we do a calculation. Now the calculation we do is a sum of all these values. I hope nobody's lost. If anyone's lost, ask questions, because that's what I'm here for. I will answer. So we're going to create a sum. So basically what we're doing is we're adding up all of these inputs to find a certain value, and then we're going to do an output based on that. We're not going to output that value. We're going to do a calculation on that value to output the calculation. So we're going to do a sum of all these values. So objects, again, object.keys, and this time we're going to run on all the inputs and the neuron for each. We'll call them K's again, K for key. And we'll say the sum, we're going to add to the sum plus equals neuron dot inputs K multiplied by neuron weights K. So remember, we set the weights to 1 in all cases here. So it's basically going to be just the inputs in this case, because we're not adjusting the weights yet. We're going to do that with training, which we haven't written yet. So basically what we're doing is we're just adding up all the neurons, the inputs of the neuron, the neuron. Okay, that gives us a sum. Now, the output. In the case, there are various ways of coming up with an output for this, but we want an output that is between -1 and 1. So we basically want to say go forward or go backwards. So go right or go left. So we're going to use a calculation called tan H. Tan H will always give you a value between 1 and -1, no matter what you put into it. So it's very useful in this case. So output, where's the output gone? There we have output equals 0. I'm going to change the 0 now to output equals math.tan H of the sum. Okay, this is going to start pulling the thing already, because it will have inputs. It already has inputs, and I broke it. Line 54. Sum plus equals. Oh, there's a mistake. Whenever you see anything like this, see this unexpected token, line 54. If you're told that the error is on line 54, it's possible that it's actually on the line before. You know, they're estimating, they're saying this is where I came across the error, but it doesn't mean that's where the error started. So in this case, I just had the wrong symbol there. So reload, and now we've got, oh, that's interesting, isn't it? Let's try that again. So why did that happen? What does it do with the sum? Alright, let's go back to the image. Right, so in order to decide what whether to output a 1 or a 0 or a -1 or whatever, the neuron needs to evaluate all of the inputs. Alright, now in our particular case, all of our weights are 1, so it's literally just adding up the values. But with training, the neuron is going to figure out that bit's unimportant, that bit there, we actually need to reverse its input. So if it comes up with 100, we want it to be -100. That one there, if it's 100, we want it to be 80, so we're going to set a weight of 0.8, so we multiply it all. And then once it's all added up, it gives you a certain number. And then we're going to just, with that number, you decide, like, is it going to be a 1 or a -1 as the output. Now this is kind of, it's kind of the kind of thing that you kind of have to get used to over time. And after a while, it kind of filters into your brain and you understand, like, what am I doing here? I don't know how to explain it very, very simply, but you kind of like have to, as I said earlier on, it's like throwing a jigsaw down and everything just falls into place. We have to do that a few times for your brain to figure it out, what's going on here. But basically, we're deciding on an output. We're deciding whether the output is positive or negative, and how positive, how negative. All right. Who is Grenian anyway? Grenian? I don't know. All right. Anyway, yes. Keep asking questions. I will try and answer. So the tan H in this case, why is it doing that? Right. So you can see it goes off to the right and then it comes back left again. Well, what is changing in this is that the X is going to the right. The angle is going to the left. The angular velocity is changing. So the angular velocity when being added, and the angle being added to the X velocity, is probably what's affecting this. It's the reason it's going backwards, is that over time that changes. It goes slightly positive and then it's slightly backwards as you add up these values, because those values are changing. Alright, now we want to start changing the weights. So what are we going to do it based on? Well, what I would do it based on in this case is that we want to actually, what is balance? Well, in this case, how can you tell if something is good at balancing or bad at balancing? In this case, I'm going to say that good at balancing means that it was able to balance for longer. All right, that's a good way of measuring things. You can just do it based on time. So if you did it for 150 seconds versus 120, the 150, whatever you had going on in the 150 was good. We'll reward that. In the 120, we'll punish that. Now what that means is that if we've got 4 inputs and we want to reward, well then we're going to be training one of these inputs at a time. If you make a change to this and it makes a better output, well then whatever change you made here, do it again. You know, that's the velocity. So you basically multiply the velocity, you make it go faster in that direction, keep going in that direction, you were doing something good. But if it's 120, then you take that velocity and you shrink it, or even reverse it, so it's backwards. Like, hold on, back off, whatever you did was bad, go back in the other direction. That's what training is. And we've got 4 different inputs in this case, with this 5 including the bias. We're going to be training against all of them. Alright. So let's do that. So before we calculate the neuron output, we'll want to do some training on it. Or, actually no, what we want to do is, first off we need to count how long did it balance. Alright, so what exactly, how do we measure how long it balanced? Well, we know that this loop gets called every time something changes in the world. So let's say that we're going to call the balance time, we're just going to call it score, okay? It's not even like seconds or minutes or hours or whatever, it's how many times was this loop iterated before the thing fell, okay? And we'll describe what fell means in a moment. So score equals 0. Alright, and we'll say that every time that the loop is called, score gets incremented, so you add 1 to it. Okay. Now, what is a fail? We're going to put in some pseudocode again. Pseudocode is when you just write something basically in English and then we'll translate it into computer afterwards. So if result of last loop is a fail, then reward or punish the bot. So what does fail mean? Fail in this case means that if the stick fell over, or if the stick went too far off the edge, or whatever. I'm just going to use if the stick fell over. So, math.abs, I'll explain that in a moment, of inputs.angle is greater than 1.3. Okay, to explain that now, the angle of 0 is straight up. 1.57 is to the right, and minus 1.57 is to the left. The ABS in this stands for absolute value. So if you have any number, absolute value means you just get rid of the negative symbols. Just like minus 30 becomes 30. 30 becomes 30. So you just basically, you take whatever's to the left of the number line, multiply it by -1, and that gives you your absolute value. So this is just a quick way of doing that. So you don't want to know if something's negative. You just want to know what is the number. What is the number in it? Forgetting about the negative or positive. So it is going to be positive. So if the absolute value of input values is greater than 1.3, then we say that this is over. This particular training session is over, or this particular iteration of the training session is over. Let's calculate whether it's a reward or whatever. Alright, so first thing I'm going to do here is console.log. In fact, I'll do what I did in my in the demo thing that I'm doing here, which is document.title equals score. And then I'm going to destroy and restart the entire session. So I'm going to call a function called destroy. Yeah. So I'm going to call a function called destroy, which is going to basically kill the entire thing. Now I need to create that function. By destroy, what I mean here is actually stop the engine, stop the rendering, and restart everything. Unfortunately, this matter library thing doesn't have an easy way of doing that. In fact, like, it has a way of doing it, but it's kind of complex. So I had to go and look this up, and I'm just going to copy paste it here. Ugly, yes. So what's it doing there? There's the function destroy. So it turns off all events, it clears the world, it clears the engine, it stops the renderer, it stops the engine. And then, after 10 milliseconds, we remove the canvas, and then we just start again. Okay, let's have a look and see if that works. Oh, nice. So, what do we got here? 76. So it takes 76 iterations for this to fall down. And then as soon as it's fallen down, it just restarts the entire thing. So it calls destroy, which does a set timeout, where it then calls initialize again. And initialize, if you remember, is the outer loop. The entire thing is inside something called initialize. So we're basically restarting the engine. Okay, so now we're going to start training it. So we decide whether the if the current run, which is 76 at the moment, if the current run was better than the last run, which was 0 or 76, then we're going to reward it. And if it's less, so if it was 75 and the last one was 76, well, then we'll punish it. Let's have a look and see how we do that. All right. So we first off need to know what was the last run. So the last score. Now I'm going to start recording things in local storage. If you remember right, local storage is, let's say I say var x equals 9. Okay, and then we do x. What is x? X is 9. Let's reload the page. Now what's x? Oops. It's not defined. Because when you reload the browser, it refreshes everything. It starts from scratch. Now you can create something called local storage. So let's say I say local storage dot let's say val equals 123. There's a reason why I'm not using x. I'll explain that in a moment. It's Alright, so 1, 2, 3. Now let's reload the page and let's have a look at local storage.val. 1, 2, 3. Now you can see it's converted it into a string. So it's not 1, 2, 3 the number anymore, it's 1, 2, 3 the actual letters, the characters 1, 2, and 3. So that's what local storage does. It records things so you can come back to it later. So if I close that, for example, I'm just going to copy that, close it, so it is gone. Open it up again, and let's have a look at local storage.val. It's 1, 2, 3. It's back. It's still there. So that's a way, it's a handy way of recording values so that they don't just get destroyed over time. So what I'm going to do here is record certain values. So let's say in the Neuron we were setting it up. See here I've got weights and velocities. Well, I would like it to read from local storage. So remember that this is a string, but this is an object. So if I say local storage dot weights equals that, well, we look at local storage weights. You can see the way the weights is written. It's a string, but it doesn't contain any information anymore. We need to actually convert it into this kind of thing. Now that's actually from a previous thing. I'm going to clear this out. Local storage.clear. Okay. So that doesn't work, because if I do weights now, then we get that. I don't want that. I want what I put in. So instead what we need to do is we need to actually convert this into the string version of that object using something called JSON.parse. Stringify, sorry, in this case. We're converting it to a string, so we're stringifying it. So you can see now we have all the objects, but they're written in a kind of a string. Now to create an object out of that, we use parse. So let's say JSON.parse. Parse means to convert into an internal object. So there we go, and now we have an actual object that we can then look through bits and pieces. So let's use that over here. So we'll say when you're setting up the Neuron, it's going to try and pull from local storage if it's there. So JSON.parse local storage dot input weights, or if input weights doesn't exist in local storage, as it doesn't at the moment, then we're going to use a string version of this and convert from that. So that's pretty simple. Now that's a pattern that you might want to learn. So if you're learning JavaScript, have a look at that and just try and understand it. Read through it a few times. JSON.parse local storage dot. Now the important, I think the most important part of this pattern to learn is that bit. It's the OR bit. So the two pipe symbol there means OR. So if the first part is blank or null or doesn't exist or undefined or whatever, then it's going to do the second part. So we're parsing the first part or the second part. Okay, and then momentum is going to be similar. It'll be JSON.parse local storage dot input momentum, or the stringed version of the object. Handily, JSON looks exactly like JavaScript. It literally is JavaScript. It's JavaScript object notation. So I can take literally an object here and just put, string marks around it, and there you go, done. Okay, so we're pulling it from local storage if it exists, but it doesn't exist yet. So now we're going to do the training. The training is where we actually put it in there. So let's go up and let's see, training. I wrote this morning. It's not in my head yet. Calculate neuron. Alright, if result of last loop is a fail, then reward or punish the bot. So this is the bit where we're going to change. We're going to change the nature of the weights. We're going to change the weights based on whatever happens. Alright, so var last score. So what was the last score before this? Because in order to know if this is better than the last one, we need to know what the last one was. So last score equals local storage again dot last score. But again, that might not be there, so we use or 0. So if the local storage dot last score doesn't exist, well, then we're going to use the value 0. And I'm actually going to set that. So last local storage dot last score is equal to the current score, which we have as score. See here, score. We're setting up score, and that's what's being outputted here. So I expect that the first time we use local storage dot last score, then it's going to be undefined, yes. And then if we reload this page, I'll just save this first. Now I expect it to be 76, but you can see it's a stringed version of 76. So that means that this actually needs to have a plus in front of it to convert it into a number. Okay. Right. Now, punish or reward. Which are we going to do? Well, to do that, we need to know a multiplier. The multiplier is basically the punishment or reward amount. Var multiplier equals 0. We started off with 0. Now, if we say that the score, the current score, is greater than the last score, then we're going to reward it. Is the live chat dead? No? Do you not see it? Everyone should be seeing this. Are you all seeing it? Good. No, you're just all very quiet. No, feel free to speak. If score is greater than last score, then reward. Otherwise punish. In fact, we're going to say if the score is greater than or equal to the last score, then reward. Because in the end, the reward, like it's all gonna cause a change, right? Reward and punish both cause changes. They all kind of move things in one direction or another. But we always want to be moving in. We want to be moving at all times. Yeah. Right. So reward or punish. What does reward mean? So in reward, we're going to say that the multiplier is equal to 1.01. Now I like to add a little bit of a random factor to it. Because if you always use the same numbers, well then you'll always end up with the same results. And I like things to be a little bit fuzzy in neural nets. So math.random multiplied by 0.01, let's say. So this will be anywhere between 1.01 and 1.02. Just grand enough. Okay. Otherwise we're going to punish it, which would be multiplier equals minus 0.9. Now I'll explain these numbers in a moment. Plus math.random multiplied by 0.01. Okay, so why did I say 1.01 or minus 0.9? Well, 1.01 means just go a little bit faster in the direction you were going. So let's say you were heading in this direction and that turns out to be the right direction. Then 1.01 moves it along that, just go a little bit faster in that direction. Whereas if you're being punished, well then it's going to go in the other direction, but you don't want to be the same amount, because then you're just kind of going backwards and forwards between the same 2 points. Always. You want it to be kind of like, yeah, you're wrong, but it's possible that you were kind of right, so we're just going to go back a little bit and see what happens. You want the values to be different, is what I'm saying. That's almost why I'm using the mat random as well. The values should be slightly different. Right, okay. Now, so which one are we going to punish? Which one? Which input are we training at the moment? Alright. Well, to do that, let's have a look at the iteration. So the iteration is, the iteration in a training is how many times have we done this training so far? And what I'm going to say is that every 10th iteration we're going to swap out and train a different thing. So at the moment we have 5 inputs that we can train. You've got X, angle, angular velocity, velocity, and bias. And every 10 iterations we're going to swap out and train a different thing. Alright? So what is the current iteration? var iteration equals local storage, there's that thing again, plus local storage dot last dot iteration, or if it doesn't exist, we're on iteration 0. Okay, now we're going to use some fancy clock math, right? So we'll say that the IDX, I'll explain this, or right, let's just do this. Var names equals X angle, angular velocity. Now I'm basically writing down the names of all the inputs here. Velocity and bias. Okay, there are many different ways of doing this. I'm just doing this like if you're going to college after all this, if college ever opens again, you'll probably learn to do it slightly different than what I'm doing. I'm doing it straight out of my head, so you know it's probably not the same way. So we want to know which one of those 5 items, 5 being an important number, which one of those 5 items are we currently looking at? So we'll say the IDX, the index that we're looking at is, we want iteration math.floor iteration divided by 10. Alright, so every 10th we're going to swap it out. So if we, let's say we're on iteration 33. Well, we want the first tree, we want to know that, but we don't care about the second tree. So we divide by 10 and floor it. So if you divide 33 by 10, you get 3.3. And if you floor that number, then you're dropping out the 0.3. So you get 3. Okay? And then we use clock math. We get the modulus of 5 against that. Now, what is that? What is the modulus symbol? You probably haven't done modulus in school. So the modulus is basically how a clock works. Clocks work on a modulus 60 basis. So if you take, for example, that it is currently 15 minutes past 2, and I was to say to you, what time will it be in 90 minutes? Well, what you're going to do is take the 90, add it to 15, that gives you 105, and then you're going to divide it by 60 and take the remainder. Okay? That's the modulus. The modulus is the remainder of when you divide one number by another. So the modulus of 5, if the modulus 5 of any number is always going to be a value of 0, 1, 2, 3, or 4. Okay? 0, 1, 2, 3, or 4. Same way on a clock, if you divide by 60 and you look at the remainder is always going to be a value between 0 and 59, inclusive. And that's useful for us here. It's useful in a lot of ways. It's good to remember this. So, what are we currently editing? Var input that we're training is names IDX. Okay, console.log. I'm just going to log this out so we can just have a look and see what we're training. I expect this to... Yeah, what am I doing? INP, there we are. I expect this to output something, and then 10 times, and then there's X, 2. I expect it to output X 10 times, and then it'll skip on to whatever the next one is, which I think is angle. Let's see. No! That means we broke it in some way. Why? How? Oh, because I forgot to increase. We need to increase this value. Okay. So if we do that, we need to increase the value. Otherwise we're going to be training the same thing over and over. Right, so now I expect it to be 10 times, and then it'll skip on to whatever the next thing is. Remember that after doing this, it's destroying and restarting. So there we go, angle. We're on to the next. So now 10 times it tells us what it's going to train, but it doesn't actually do the training yet. Let's do the training. So first off, I'm going to comment here. Let's see. Just what are we training? Okay. And then, right, now we do the training. Train the thing. So, training in this case involves changing the multiplier of the weight. So we're changing the weight, which is fairly simple. Like, we're basically going to say neuron neuron.velocities input training. We're changing the velocity multiplied by equals, so we're multiplying it by the multiplier. That was simple. Okay, now I'll go back to momentum in a minute, but we're just going to use, we're going to ignore NEU. We're going to ignore momentum, but we'll come back to that. Neuron.weights, this is the important one. The weights is the thing that actually gets multiplied by things in training. So which weight are we changing? We're changing the one of, in this case, velocity. We're going to add to it the current velocity. Neuron.velocities in training. Fairly simple. And then after we trained this, we want to record. We want to record what changes we made, so that when next time it loads up, we'll actually use that. Now this will be interesting because this actually pretty much is a neural net. This is pretty much it done. So let's say local storage dot. Have we set? Yeah. Okay. Input weights equals. Now remember, stringify. So we want the string version of it, of neuron.weights. So we're stringifying all of the weights. And then we're going to just do the same for velocity. So I'll just copy. Of velocity. It's actually plural, so velocities. Keep it right. And I'm going to record the momentum, even though we didn't change the momentum or use it. Okay. And I'm going to take all this local storage stuff here and move it into the same place. So we're recording everything in the same place. So what we're doing basically is we're going to train something for one iteration and then record what change we made. Alright, let's have a look and see what that does. it breaks everything. Line 68. Whoops. 68. Unexpected token. Oh. There. Unexpected token U in JSON at position 0. 104. I'm pretty sure I know what I did wrong here. Let's just check the local storage and see what actually got recorded in it. Input momentum's undefined. Yeah. So let's see, that was this here. Neuron.momentums. Oh, that's because it's not called Neuron momentums here, it's called Neuron momentum. So we'll put the S there, and I'm just going to clear out this local storage again. Clear, clear, clear. So that it is empty, and reload. See what happens now. Okay. Now I don't know if it's actually doing anything here. So what would be interesting here is if we could see the input velocities, which are what I expect to change. See up here in the training we are changing the velocities of the neuron. So I'm going to just put a console log here of the neuron velocities. In fact, I'll put it up here where just after I've changed it. And we'll see what it actually does here. So, reload. Everything is 0. Why is everything 0? 0 is useless because if you multiply 0 by anything, you still get 0. So, I've obviously screwed something up somewhere. Alright, so let's try clearing that up. And reload. Okay, angular velocity, velocity, they're all 1, but the x is 0. That means that that this here somehow multiplier is 0. So multiplier is 0 here. Oh, I keep making this mistake, and I don't know why, but multiplier here, I just missed the I. There we go. So it actually started as 0, but it never got changed to a real value. I'm just going to undo, clear this up again, and start again. Now let's see what happens. Now you can see that the x is changing. Now we're still getting 76 per iterations. Oh, 75, so it's actually getting worse now. But look what happened there. After it got worse, it did a punishment run, so it's at 0.99 here. Now it's 76. So it's basically going through each of these and doing 10 iterations of each of them. Multiplier, thank you. The falling looks more realistic physically, yes. What is it training right now? Velocity. It's training velocity, which is the second last. Okay. I'm going to put those two console logs onto one line. I'm obviously dying here of something. Okay. Now, we're training X. 88. It's getting better. Look at that. Look at that number. It's getting better. A 91. So we see what's going on there. It's very, very gradually getting better and better. Oh, look at that. So it needs to figure out now, how do I stop and go back? 165. 180. Oh no! Yeah. No, it's just a cough. Yeah, so COVID. Ouch. Oh. I got a paper cut yesterday and it keeps hurting me. COVID-19, one of the symptoms is a dry cough. This is not a dry cough. 141, 247, that was good. Now, this, I believe, is going to make a mistake in a minute. See, it's very gradually learning to balance, but it's also moving off to the right. But we didn't tell it to stop moving off to the right. 226. I think it's going to go right off the edge in a minute. Do we all understand what's going on here yet? Like, does everyone understand exactly how this has worked? Do you all understand this? Yep. Okay, Amit understands. It's kind of a complex idea to get into your head, but you know, once it's in there, it actually helps you in quite a lot of ways. If you're doing a lot of really complex programs, you can use the same concept, even if it's not neural networks. Like this technically is not a neural network because there's actually no network. It's just one neuron. So it's not really a neural network. But I've used the same concept to do things like recipe generators. I think I do. The best way actually to learn something is to either do it yourself or to teach somebody else to do it. So maybe in order to learn this, are you all actually learning programming languages or just listening in? I wonder if you're all practicing. Like, is anyone doing? Like, I know I'm doing this in JavaScript. It's a neural. It's not. Yes, it's just a neuron. I know that, like, I'm doing this in JavaScript, but you could be doing this in whatever language you're practicing. Like Amit, I think you're doing C#. You could be doing this in C#. Is anyone else doing any other languages? Yep. Alistair, are you there? I know Alistair was doing Python. So you could do this in Python as well. I think there are some visual languages for Python. 147. So I'm expecting this to very gradually get better. Now, I think what I like watching in this is the velocities. The velocity is basically how quick it's changing certain training values. I expect that as it gets closer and closer to the optimal value, that the number would get smaller and smaller. So if you see, for example, this angle here, 0.657, I think that means, wow, look at that. Ha! Look at that. I think we got it. Anyway, the angle here of 0.65, if this was still training, this is amazing. It's just kind of stopped. It's very still. It must have found the exact right way of balancing it. You know what the next step is? The next step is we actually build a robot that does this. An actual physical robot. That'd be interesting, wouldn't it? I mean, we could even use the same code here. I mean, you've got x, angle, angular velocity, velocity. All of these can be calculated. It would be a lot trickier now. But we basically did this. Like, we did this in 1 hour and 4 minutes. So, yeah. Okay. We made a robot that can balance a stick. Alright. In 1 hour and 4 minutes. To do this in real life would be a little bit trickier because we kind of short-circuited things. We looked at the stick's values because we have access to that. Balance bot balances your phone on a stick. Yep, if we're not wiped out. We could do this. In fact, what are those things called? Hoverboards, which don't really hover and they're not really boards. They use something similar to this. I'm not sure if they use a neural net. They probably use the actual. There is a way of just calculating using, you know, calculus. What are the correct acceleration and velocities to use in order to balance these? They probably use that. But this shows you that you don't need it. I mean, I don't know the formula that you'd need to come up with the correct calculation or correct velocities to balance this. But I don't need to know, you know? We basically made a neural net. I just told it, here, try a load of things until it works. And that's basically what it did. I could put more inputs in this. I could put less inputs in this. It's using 4 at the moment. X, angle, angular velocity, velocity, and bias. 5 inputs. We could do it without 1 or 2 of them. In fact, my original demo of this had only the angle and the velocity. And that just worked. You could probably get away with just the angle. But the more information it has, the better it can make. The better it can make the network, the neural net. So I'm just going to show you some examples of other things. This actually, what we've done here is kind of complex because the most simple neural net is actually simpler than this. There's a very simple kind of neural net called a forward feed network. And the forward feed network is how, for example, you would identify whether a picture is of a flower or a dog. A feed forward network. In which case you have, let's have a look at a picture of a feed forward network. Feed forward network. Feed forward neural network. Right, I'll find a picture and let's find images. There, that's a good one. Right. So a feed-forward network basically takes a load of inputs. Now you can see it's 1, 2, 3 here, but if you think of a picture is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's all the pixels. If you give them all a single number, you can basically say that it's pixel number 20, it's pixel number 400, whatever. It doesn't really matter the actual X or Y location of it in the image. Now what happens here is that what we have in our case here is one of these connected to a load of these. So we've got X, angle, angular velocity, all connecting to one of these, which is giving one output. So it's not really a network, it's a neuron. Now a network is if you take one of these, and another of these, and another of these, and another, and they're all training off the same inputs, and they're all giving different outputs. But those different outputs act the same as these. So it's as if you were to, I can't put my hand on this and hide that. Right, it's as if you were to do it again, but this time do another output, just get one output. So in this case we have 2 outputs, and you could have, for example, flower or dog. You might have a picture which looks like maybe it's a dog in a flower output, a flower costume. So is it a flower or is it a dog? The answer to that is yes. So that'd be 1, that'd be 1. So you could have another one which is that it is definitely a dog. So dog would be 1 and flower would be 0 or -1 if you're using what we did there. What's going on? I hear a printer acting up behind me. And the other way around, the dog might be 0 and the flower might be 1. Alright, A-E-I-O-U. So a neural network is where we take what we already built and we take a load of them and stick them together and come up with an output. So in order to build a flower, to identify as something a flower or a dog, then you'd need something a little bit more complex. So let's say that's the same picture as before basically, but these are the inputs, and then we have a hidden layer, A hidden layer is basically a layer in the network that we don't know what it's doing, but it's kind of needed for this. It's like in your eye, for example, when you see something, it actually, the data from the eye goes through a load of hidden networks, hidden layers, before it hits the back of the brain, and it basically says you're looking at a dog, you're looking at a flower. So it's doing a lot of little complex things that could be abstract things like it's got angles, or it's got high contrast areas, or that looks rectangular. We don't know. We don't care. Alright, so basically, let's go back to this again. It's not training anymore because it is trained. Now, if I reload this, I wonder. Let's try it. It's fantastic. Oh my gosh, that is so fantastic. So I'm just going to close this completely, open a new page, and paste it in. Go! Isn't that fantastic? So it's after learning, and it's recorded what it learned, and it knows how to balance now. Now, just to let's give it a challenge. I'm going to change the shape of that triangle. So let's say I change this to -1. So this is basically going to, we'll change this to, it's going to change the balance of the stick. We'll see what happens. Did I change the right one? Reload. There, right. So the balance has changed. But it knows what to do. Let's move this very far out. That's fantastic. It knows how to balance it. Could you add tools like nudge? Yes, I was kind of looking at that 2 weeks ago when I started doing this, but I'm not familiar enough with Matter.js to know what to do here. Now, what I could probably do is, I don't know. You see, I'd be basically learning on the fly here, and it could take half an hour, it could take an hour, and I'd be wasting my time, wasting yours, because I might fail completely. So you'd be basically watching me not do anything. Yes, we could add them, but I have to figure out how does it work. It is possible. I know that Matter.js has tools for mouse interactions. It has demos. Matter.js documentation. So let's see. Demos. Demos. Now, so yes, you see I can drag that around, which means that yes, we can do interactions, but I haven't figured out how to do that yet. Woo! I'm sure the code is probably simple. Just click on that and see. Yep, it looks like it's just doing a load of random things. Yep. So it could be it could be just as simple as adding that in. I don't know. I'm gonna give it a shot. At the click of a button. Yes. Yeah, but you know, angular velocity, normal velocity, velocity of which point. Let's just add this in and see what happens. I don't know where to add it in, but let's just play around. Var mouse equals. Just add that in there. I don't know if this is going to work. Now, I can't just use mouse. It has to be matter.mouse, and this has to be matter.mouse constraint. 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 Right. This will be interesting if it works. Now we need to add it to the world as well. So we'll just actually move this up above the bit where we're adding bits to the world. And just add it in. I don't know if this is going to work. Let's try it. Oh, look at that. Oh, that was too far. Oh, that's not to forget. Oh, there we are. Hey. I tilted it so far that I forgot how to balance itself, but it's learning again. Alright. Okay. So, I think what's happened here is that it knows how to balance from basically a still start. But as soon as you give it too much of a jolt, it forgets. Or it doesn't know how to recover from a big jolt. But you can see here it's trying. And it'll probably get back pretty quick. So it's just continuing to learn again. Now remember, like you can go to this address. It's right there in front of you. You can go to that address and see it for yourself. That was pretty simple, wasn't it? I mean, I did break it, but... Alrighty. It's getting punished for something that isn't its fault. Yes. Yes. I mean, it's kind of like that Boston Robotics video of the robot dog being kicked. You have no morals. Sorry. This is literally life. Yeah. Yeah, you get kicked for doing your job. If you do your job very well, it is kind of like real life. You know, if you do your job very well, then your boss will give you more work to do. You kind of have to stand up and say, look, this is how much I'm doing. I cannot do any more. Yeah. Alright. So, anyway, alright. I'm expecting that, like, this will... You can see it's going up again, 196, so it is getting better. It will learn to balance itself again. Any questions? 13:17. I know it's a bit quicker than usual. I didn't expect this to be so quick. Any questions about this or anything else? Do you think we should... I wonder, should we actually... could we make this in real life? I don't know if we could do it in 2 hours. I know that, like, do you watch... Adam Savage has a show, Tested, where he does one-day builds. I mean, he would be basically... There we are, it's balanced again now. Woo! Excellent. Let's break it. It is learning to balance itself. Like, that's awesome. That is really awesome. Right, not a question. Okay. 2 months. What do you mean? What do you mean by 2 months? Alright, I'm playing Universal Paperclips and I've got enough production to sell paperclips at 1 cent. What are you going to add to enhance the realism? Nothing, really. I mean, I don't care about this. I could destroy this and just walk away. You know, it's not really... I'm not doing it for the realism. I'm trying to illustrate a point, like that this is how a neural network works. I mean, yeah, you could make games with this. People have made games with this, so yeah, you could make this realistic. If you wanted to make it really realistic, then maybe add in 3 dimensions. That's 2-dimensional at the moment. So that's a 2-dimensional object. I mean, to make it more realistic, in fact, we have been kind of talking about this. To make this more realistic, I could make it in real life. You know, we could make an actual, like, if you look at this thing here, basically, it's kind of like these 3D printers behind me. You know, you've got a belt, and then you've got a carriage, and there's something balancing on it. So we could make this in real life. Now the question is, how do we get the values from this? Because in order to get the values like the position and the angle and the angular velocity, we cheated in our case because we looked behind the scenes. We looked at the engine and said, well, it says it's at angle of 1.4. It says it has an angular velocity of whatever. So we can't do that in real life. You know, you can't look at something and look at its stats. That's an anime thing or a manga thing. But what we can do is we can probably figure it out by doing some tricks. So, for example, if we got a stick and we paint the top of it green, or in some color that is not likely to be in your environment, then if you have a camera and it sees green, then that green is the top of the stick. I just heard about it from you. Yeah. So yeah. So there are ways of looking at something in real life and calculating its position. Now it involves trigonometry. Learn your trigonometry. It's very good. I've only been playing since the start of the stream. You're in for a treat. I mean that game, it gets weird. You know, you might think you're just selling paper clips. It gets weird. Yeah. What is it, Amit? Release the Thunder Drones or something, is it? I've only been playing... No, you have not. I think it's released the Thunder Drones. Right, any other questions? I mean, yes, we could do this realistically. Yes, we could make it more realistic by making it actually real. Any other questions? It would be interesting, though. There's still too much of a lag between people saying things. Release the Hypnodrones, that's it. Release the Hypnodrones. Okay. Right, I'm going to kind of wrap this up then. I don't know what we'll do in the next class. Next stream, 2 hours of paper clips. Yeah. No. I mean, yeah, we could make a game like that, but it's kind of been done. Okay. Is that what you want? We're going to make a game like that then. What are we going to trade in? What are we going to trade in? I mean, paperclips has been done, so we'd have to do something else. We could do paper. And with paper you need trees. Doritos, you need corn. And spices. You can't have Doritos without spices. Yeah. Is that the consensus now? Or should we go on further with neural networks? I mean, it would be interesting to look at pictures of dogs and cats and see if you can tell the difference. Make a game where you have to try to knock it over. Oh, knock over what? The stick? Ah, now we're getting there. Yeah. Yeah. Let me think about this, because actually, like, you might be onto something there, like a game where you have to knock over. I wonder. How about no, this could be interesting. How about a game where you have to balance something, and you have to balance it while, like, you could think of this as a scroller game. If you remember the old scroller games where you have like things coming in from the right side and you have to avoid them, but what if you have to avoid them while balancing something? Like, let's say a game where you're playing a waiter in a restaurant and you have to balance stuff on the plate. And meanwhile, you've got other robots which are also balancing things on plates, and they have to avoid you. You know, like, that could be an interesting game. And meantime, there are tables and people, and the people are like, over time there are more and more people, and you have to avoid them all, and each one of them is nudging you, their elbows are touching you. Trade universes. I mean, it's a big idea, but you know, maybe too big for 2 hours. Also, the graphics. I mean, yeah, it could be too big. The graphics have to. You have to be able to see what you're doing. Play as an engineer restoring the leading tower pizza in the future. That's yes. Yeah, it'd be like Jenga. A game of Jenga on a moving platform, where you've got a robot that's actively trying to balance the Jenga while you're taking bits out. Alright, guys, I'm going to give you all homework. I mean, you're all looking at this game, Universal Paperclips, and you want me to build it. Well, I think it's a simple game. I want you to build it. So, Amit, I know you're good at Scratch. I know you're getting there in C#. How about you write something in C#? You know, so we can all look at it. And what else? Who else have we got here? Bowen? Scratch, maybe? I don't know what else anyone else is doing, but you know, if you don't know any programming languages, try and learn some Scratch or JavaScript, what I've been doing here, or try and learn something. And have a look at the Paperclips game. I think, if I remember right, that I looked into this before, and I think that the Universal Paperclips game was actually made by a guy that wanted to learn how to program. So you could do the same. You know, you've seen the game. Okay. Alright, Amit, you're going to do Scratch. I want to see you do this game. I want to see this game. You know, Jazz, great, there we are. And obviously, if anyone needs any help in these things, you know, I'm on Facebook. Or send me an email or whatever. You know, ask me questions. That's what I'm for. If you, like, you have to, like, I want you to build something and show it to me. And I don't care if it's good or bad. I just want to see something. You know, and then we can have a look at it, and we can maybe, if somebody comes up with something really cool, we can maybe do a riff on it. We can do a version of it, maybe push it a bit further. I will try my best. That's what we want. Do your best. Kampai. Right, got a new Scratch account. Yes. I wonder, has anyone else made a Universal Paperclip Scratch game? It might be in there, but I wonder, could you use this for your project, for coolest projects? Because I know that they're, I don't know how that's going to work. They want you to put this online. I don't know how that's going to work. Deus Creations. The Scratch Master is watching. It's not me, whoever that is. It's probably Joe, is it? Who's the Scratch Master? Who's Grenian? Grenian, who are you? Gangster JF, let me think. Andrew, I think you said. We've got Amit, we've got Bowen, we've got Evan. Yeah, there's a lot of idle games out there, and they're all pretty simple to do. I mean, there's a lot of tower games. If you look at the idle tower games. There's also tower defense games. They're pretty simple to make. Owen. Right. There's tower defense games. All of these are really, really simple to make. They're all simple ideas. They're really simple to make. The tower defense one is probably... There's a bit of geometry and trigonometry in that. But other games like the tower idle games, they're pretty simple. Anyway, alright. So we'll leave it at this, and I want to see some homework. I want to see something from someone over the next 2 weeks, and then we're gonna have a look at that in the next class and maybe expand on it. In fact, I might do tower defense games. Has anyone played tower defense games? I'm going to write a tower defense game in the next class. Alright, it's going to be pretty simple. You'll see what I mean. It's really, really simple. Make an idle game. Yeah. Or a stick balancing game. I'll do a tower defense game because they're pretty simple to make. The balancing game that would take hours and hours, probably days, to do it properly. I mean, we have a balancer here. It basically took us in total maybe 2.5 hours. 1 hour in the last class and 1 hour in this class. But a tower defense game you can probably do in 1 hour and have it working and have high scores and actually be usable. We'll see. We'll see. Okay, so I'm going to leave it at that, and I hope you all got something out of this. And I'm going to end the stream now. So, see you in 2 weeks.